Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's challenging level puzzle, and it's called Rat Run 38 Synchronicity by Marty Sears. And here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. Aim of experiment. F and P must both reach different cupcakes by finding a path through the maze. The paths must not visit any cell more than once, cross themselves or each other, or pass through any thick maze walls. And in this puzzle, there is no space to move diagonally in this maze. So you can only move orthogonally, or basically horizontally or vertically. And you cannot visit any cell more than once. You cannot cross each other's paths, or your own path. And you can't pass through any thick maze walls. We have black courants, where if two digits are joined by a black courant, one is double the other. So say we had a 2 here, then this would be 1 or 4 to maintain the one, make sure that one is double the other. That's how black courants work. We have a one-way door, where the purple arrow always points to the smaller of the 2 digits it sits between, and may only be passed through in the direction it's pointing. So neither rat can go through this one-way door. This one-way door going this way. It has to go going this way. And the smaller the arrow points to the smaller of the digits in these two cells. So this cell must basically always be greater than this cell. So that's one-way door. Test constraint. In this experiment, any 2 digits visited adjacently along a path must be different parities. That is, one is odd and the other is even. And also have a difference of at least 5. So, there's two one-way doors. So that's why I guess we'll label her P and her F. P cannot go straight this way because she would be going through the one-way door the wrong way. But along every path, these 2 digits must be different parities. Any 2 adjacent digits must be different parities. And they also have a difference of at least 5. So, for example, if this were, say, a 3, this would have to be an 8. Because the digits, again, have to be different parities, and 3 is odd. And normally, the digits that are 5 or more away from 3 are 8 and 9. But the problem is 9 is the same parity as 3, so therefore cannot be here if this is 3. Anyways, those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, so we know P cannot go anywhere except this way. So, let's color those. So she has to go this route. Well, so they have to be odd. So it has to be odd and even, different parities, and you must be able to go. They have to be different parities, and they have to have a difference of 5, which is similar to the Whisper 5 lines. So let's color this orange. We'll make this yellow. This must be orange. So the oranges have to be the same parity. And the yellow has to be the opposite parity. And the opposite must be 5 or more away from the other parity. Okay, that's interesting. So technically, so F could just go straight down there. That would work. P could go that way. This digit is next to two unique digits on a whisper 5 line, essentially, and it must be opposite parities of the other. So what we cannot have here, this has to be 1, 2, 8, or 9, right? 2 could be here next to 7 and 9. 1 could be here next to 6 and 8. Okay. Technically, she could go this way. Does that work? The thing is, what happens if that is the case? So yellow, orange, and yellow. So yellow would be the same parity. We know 5 would be... 5 can never be on a whisper 5 line, because if you subtract 5 or more from 5, you get 0 or less, which is not a normal Sudoku digit. If you add 5 or more to 5, you get 10 or more, which is not a digit. So, we would have to have 3 even digits somewhere here. It would have to be, and therefore one of them would have to be 4 or 6, which can only be next to one unique digit on a whisper 5 line. So the 4 or 6 is going to have to be either here or here. And that would be next to 9 or 1. Could this ever be 4? If this is 4... Oh. The problem with this... Right. So, the problem with doing this is... Okay, that makes sense. So the problem with doing something like what I did here is that we would have to have 3 digits, all the same parity, and all either all high or all low. Because on a whisper 5 line, you'll always alternate between a high digit and a low digit. And if you want to find out why, you can go to one of my Learn How to Sudoku videos with a whisper 5 line in it. But basically, because we know you alternate between low and high digits, these are basically the same parity, and they must be the same set of digits, high or low. But the problem with this, so if P ever goes back here to try to reach this cupcake, she's always going to have another orange here. But that means we have to have 3 digits, which are the same parity and the same high or low state. But the problem is we can only have 2 of those, right? There's only going to be 2 even cells that are both low and 2 even cells that are both high. Same with 2 high cells that are both low and two odd cells, which are both low, and two odd cells, which are both high. We have 1 and 3 as the low odd cells, 2 and 4 as the low even cells, 6 and 8 as the high even cells, and 7 and 9 as the high odd cells. But you can't ever have 3 of the same parity. So therefore, you're never going to have 3 of the same set here, which is orange and yellow, right? So therefore, P can never reach this cupcake. She always has to reach that cupcake, because you can never go diagonally. So you'll always go in a checkerboard pattern. You'll always alternate between orange and yellow, orange and yellow. But for her to get to here, it would always have to be yellow, which means the one reaching that has to be orange, and we're guaranteed then that she has to have 3 oranges in this box, which have to be the same parity and the same high or low situation. And that's never going to happen. So therefore, once she gets to here, this digit can never be the same parity. So that means that means F cannot go this way. F has to go this way, and she has the same problem now. So it's green, pink, green. We'll use for her coloring. This could be yellow. 1, 2, 3. So green, pink, green, pink. So pink, green, pink, green, pink, green, pink, green, pink. So the thing is, because you can only go horizontally and vertically, and you always alternate between the odd and evens and the different parities, one thing we know is you can't have more than 2 on the same row or column or box that are the same parity and the same high or low. What do we usually call it? Entropy? Yeah, entropy. Interesting. So because of that, but we know that to get to this cell here, which F has to, because P cannot reach that cell anymore, so P has to reach the cupcake here. You'll always alternate between the different parities and the different entropies. So we have green, pink, green, pink. Green, pink, green, pink, green, pink, green, pink, green, pink, green, and then pink. So this is always going to be a pink cell. Okay. Same with this. Orange, yellow, 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 orange, yellow. So that's always going to be yellow. Okay. Okay, what we're going to have to do then, the path, again, you can, the rats cannot go on more than 4 cells in the same row or column, because they're always going to alternate between low and high, and the same pair. They're going to have to also alternate between the same parities. And you can't, again, you can't have more than 2 of the same parity in the same row or column or box, and the same entropy, right? Low or high. Because if you have low 4p, she's only going to be on the same orange cells and the same yellow cells. And those orange cells are going to be odd and low or odd and high. And the other one must be the opposite. They must have to be. So if she goes on odd and high, she must be on even and low for the other set. So because of this, she can only go at most 4 here or at most 4 here. She can't go any more in this box. She can't go any more in this row. So therefore, she would always have to go that way. And it's the same for F. F has to do the same. So she goes either 4 here and then goes here, or 4 here and then goes there. Either way, she cannot go this path, because if she goes that way, they would have to be 5 or more apart from each other. And there's no 2 digits that are ever 5 or more apart. So she can't go back down this way, because then that would be too many cells here. That would be the same entropy and the same parity. So she has to go this way. So then she goes that way. She can't go this way for the same reason. She could technically go back here, but if she goes here, that's 3 greens, and that's not possible. So she can't go that way, so she has to go that way. Whoops. She could go here, that's fine. Or here, we don't know. One of these is yellow. The digits that can be next to a black Kropke dot cannot be 5, 7, or 9, essentially. Because 5, 7, and 9, if you have them, you get 2.5, 3.5, 4.5. And if you double them, you get 10, 14, or 18, and none of which are digits. So these have to be 1, 2, 3, 4, 6, and 8. So the only high digit here can be 6 or 8. Which means the low digit here, which has to be next to it, has to be 1 or 3. So this is guaranteed to be 6 or 8 next to 1 or 3. One or 3 is going to be in a 1-to-2 ratio with 2 and 6. So obviously this can't be 6. 6 can only be next to 1 on a Whisper 5 line, which is essentially what the test constraint is. And it can never be next to 2 unique digits on a Whisper 5 line, and these are unique because they are in the same box. So, and we can't have 3 here for the same reasoning. If this were 3, it would have to be next to 2 unique digits on the Whisper 5 line, but they would both have to be even, and 3 cannot be next to 6 because that's not 5 apart from 6. So this has to be 1 or 8 here. So if this is 1, this has to be 2. If this is 8, it has to be 4 here to be in a 1-to-2 ratio. If this is 1, it's next to 6 and 8 here. If this is 8, it's next to 1 or 3 here. So we know we are guaranteed an 8 here, and we're guaranteed a 1 in one of these cells. So one of these is 8, and one of these is 1, so this cannot be 1 or 8 here. Hmm. Um. Hmm. So F is going to have to go on high evens and low odds, because that's the only way that these work. that means P, because she's the opposite, she has to be the opposite because if she's not, if she's exactly the same parity and the exact same entropy as F, then there would be too many digits in this box and in this box which have the same parity and entropy, right? We'd have to have 3. So that's why, so therefore, F has to be high evens and low odds. So she's always going to be 1, 3, 6, or 8 here. And she has to, therefore, P has to be on low evens and high odds, because otherwise this isn't going to work. So she's going to have to be 2, 4, 7, 9. Obviously, 9 cannot be here. 1 can't be here because these digits can't have to be greater than this one. So if orange is the odd highs, this has to be 7, and this has to be 9. If orange is the low evens, this has to be 9 to be next to 2 and 4. 7 can't be next to 2. Same with, you can't have 6 here, you can't have 3 here. So this is 1 or 8 there. If this is 1, this has to be, I think, 8. Because if it's 6, it would be guaranteed to, it can't be next to 2 1s in this path. So this is 8 only, if that's the case, which means this can't be 8. That's 6 if it's even. 3 also can't be next to both 6 and 8. So this would have to be, this is 1, 8 as a pair, which forces that to be 3, 6. This can't be 4 next to 2 unique digits on the Whisper 5 line, so that's 2 or 9. Same with this. This is 2 or 9, which makes this 4 or 7. Well, this can't be 3 anymore. So we know this has to be 6 or 8 to be greater than this digit, which means pinks are even. And pinks have to be even and high. So this must be 8 here. This must be 8 here. That's next to 1 and 3. That means this must be 1 and 3 as a pair. That eliminates 1 and this digit in a 1 to 2 ratio with 1 or 3 is 2 and 6. 8 can be in a 1 to 2 ratio only with 4. We know this is 2, 9 as a pair. This is 6 or 8. So we have to have a 6 somewhere in one of these two cells. So, because that's the only way that her F's path can move. Because we can't have 8 here. We can't have 8 here. So either way, one of these is going to be 6, which means this can't be 6, which is 2, which makes that a 1, and that is going to be valid next to be next to a 6. 1 eliminates 1 there, so it's 3. 3 cannot be next to 6 on the Whisper 5 line, so 3 has to be next to an 8 again, so she's going to have to go that way, and that's an 8. One of these is 6. 2 eliminates 2 in the rest of this row, so this can't be 2. One of these is going to have to be a 1 for F to continue on the path. So we know there's a 1 here. We know there's a 6 here. One of these three is going to have to be a 6. Can't be here. Can't be here because if either way, I guess no, it could be 1, 6. Can't be here because if we go 1, then 6, we can't go 1 here, we can't go 1 here, we can't go 1 here because this 1 sees all of them. And then this 6 would be stuck. So the 6 has to be one of these two going this path. Oops. And then would have to go to another 1. So could be going 1 over there. We do know 1 has to be one of these 3 digits here. 3 has to be one of those 3 digits here. Where's 2 in row 1? It has to be one of those 3. And 8 has to be one of those 3 digits there. Because of these cells here. Remaining digits in box 2, we have 4, 5, 6, 7, 9. No 4 here, obviously. This digit, no matter what, is going to see either this 6 or that 6 there. So this cannot be 6. So I think this has to be 6, right? If we try to have this as 8. No, it doesn't have to be. Never mind. It could be 8. Remaining digits in row 9. We don't have 2 or 9 available because this must be a 2-9 pair. So we have 1, 3, 4, 5, 6, 7, 8 available. No 3 available here, no 8, no 1, no 1, 4, or 8 there, no 3 or 8 here. Because of the digits in the columns. This digit has to be 2 or 9 also. Because whichever digit connects these with this has to be the other 4 or 7. And if it's 4, obviously it has to be next to 9 and 9. If it's 7, it has to be next to 2 and 2. So that's the only reason why this... So we know this is 2 or 9 also. Whichever digit is connected to this, it has to have a 1. It has to be 1. Because it must connect 2 digits that are going to see each other. They're going to be in the same box or the same column or the same box or the same column. So 1 is going to have to be one of these two. We cannot go 1, 6 here because then the 6 has to go to another 1, but it's not going to be able to go to 1 here, here, or here if the 1 is here. So therefore, we know we have to go this route. So that's a 1, and it can go 6 to either of these, then to 1 here. We can't go back up because the problem is that would be too many digits again in the same box, which have the same parity and the same entropy. Because these would be all the same type. So you'd have all 3 pinks there. You can't have 3 pinks in the same box. So if we tried 6, 1, 8, 3, you have to go that way. So she cannot go that way, can't go that way. It's either go here and then that's 1, or here and then that's 1. So either way, this is going to have to go that path. So that's 1, which eliminates 1 here. One of these is going to have to be 8. And then we'll have to go to a 3 in one of these two cells. Because if we go 3... Oh. So how does that work? Okay, so if we try going 1, 8, 3, that's not going to work either, because the problem is none of these can be 8, and the only digit which can be next to the 3 on F's path is an 8. So she cannot go 8 there. She's going to have to go 8 here. You could go 3, 8, 1, 6, so that is possible. Or 3, 8, 1, 6. So either way, this is going to be a 6. She's going to have to go along this path. So that's 8. One of these is 1. One of these is 3. So 8 eliminates 8 in the rest of the column. So where is 8 in row 2? 8 has to be here. That means 3 has to be one of these two digits here. 1 is one of those. Remaining digits of this lower right-hand box, we have 1, 3, 4, 5, and 7. 1 can't be either of these. This cell will see both of these 3s available, so this cannot be 3 there specifically. 6 is greater than 4. So this has to be 4 and is even. So the oranges are even and low. The yellows have to be high. So then that forces this to be 2. That's 2. This is 9. We have a guaranteed 7 here. 2 is greater than 1. So this is 1 here, which eliminates 1 being here. So then the path has to go this route, which is the 1. 4 eliminates 4 in the rest of the box. 1 eliminates 1 here. So where's 1 in row 3? It can only be here because 1 can't be here because of 1's in the boxes. 1 can't be here because of 1's in the columns. So we have a 6 here or a 6 here. And a 6 here or a 6 here. Okay. Where are the 8s? We have in row 5, 8 has to be one of those two. In column 6, 8 has to be one of those two. Interesting. 2 cannot go to 1. So either way, whichever way 2 goes, it cannot go this way. It has to go either here and here. And can't go back to here because then there's too many cells in row 9, which are the same parity and entropy. So she has to go this route. So this must be yellow, which is high and odd. So this cannot be 8 here. This must be 7. That makes that an 8, so she cannot go that way. She has to go this way. So this is yellow and is 7, which makes this 5, which makes that 3. 3 eliminates 3 here. Where's 3 in row 2? Cannot be here because of 3 in the boxes. Can't be here because of 3 in the column. That's guaranteed to be an 8, so 3 has to be there. So 3 cannot go that way. So then F has to go this route. So that's 3. 2 and 7. No, this can't be 7. This has to be 9. But either way, this is still going to have to be 8. So that's fine. But this has to be 9. Because either way, one of these is going to have to be a 4 next to it. So again, this is 8 now. The path has to go 7 there. This is 5. That's 3, which eliminates 3 there. That makes that 3, so this can't be 3 there. So then the path has to go through here, and the path has to go through there. So one of these is a 4. We're not sure which. There's no more 4s available in row 9. No more 8s available in row 9 either. This can't be 1. So 1 has to be one of these 2 digits there. 4 cannot be here because of 4 in the box. So 4 has to go this way, which is orange. It can be next to a 9 only on the path. So then it has to go to 9 there. We can't reach a 4, so one of these is going to have to be 2. 2 cannot be here because of 2 in the column. So 2 has to be there, and that's where the path has to continue. Remaining digits, this can't be 4 or 9. In column 5 is 5, 6, or 7. Remaining digits in box 5 are 3, 5, 6, 7. Okay. Box 8 is also 3, 5, 6, 7. No 5, 6, or 7 here because of 5, 6, or 7 in a row, so that's 3. No 3 here, no 3 here, no 3 here. We have a 5, 6, 7 triplet in column 4, which eliminates 5, 6, and 7 in the rest of the column. No 5, 6, or 7 here, it's 9. That means the path cannot go this route. It has to go this route. So that's pink. 9 eliminates 9 in the rest of the box. Remaining digits of row 1 are 2, 5, 6, 7, and 4. 2, 4, 5, 6, 7. No 2 or 7 here, no 5 here, no 4 or 6 here because of digits in the columns. Remaining digits of column 7 are 4, 5, 6, and 9. No 4 here because of 4 in the row. No 6 here because of 6 in the row. Column 8 are 2, 4, 6, 7. No 4 here because of 4 in the row. No 2 here because of 2 in the row. Remaining digits of column 9, we have 2, 3, 5, 7, 9. No 2 or 9 here because of 2 or 9 in the row. No 3 here because of 3 in the row. And box. One has to be one of these 2 digits in row 6. We have to have a guaranteed 2 next to the 7 or 9 because 4 is not going to be next to 7. And if it's 4 here, it's going to have to be between 2 unique digits either way. Same with that. So this is going to have to be 2, which means this can't be 2 because of 2 in the row. So 2 has to be here. And this must be orange. And then we go to one of these as yellow. We don't know which. Remaining digits of box 1, we have 4, 5, 7, and 9. Okay. 2 eliminates 2 here. Two is going to have to go to a 7 in one of these cells. Don't know which. Then that's going to have to get to another 2, which cannot be here. Can't be here. So we can't go to 4 here because we have a 9 there. So it's going to have to be 7 and 7. Can't go to 2 here. It has to go to 2 here. So that's 2, which forces that to be 8. This is on the path. 2 has to then go to 9 in one of these 2 cells. And then that's going to have to go to 4, which can't go here, cannot go here. So that means it's going to have to go here. So this has to be the 9 connecting to the 4, connecting to the 9, which connects to the 7. That's 5. And this has to be the path. So that's yellow, orange, and yellow. That means this can't be 9 here. Where is the 9 in row 8? Cannot be here because of 9's in the column and the rest is filled, so 9 has to be here. Whereas 8 in row 8, it can't be here because of 8 in the column, so 8 is there. That leaves the remaining digit as a 4. Okay. 6 can't be here because of 6 in the column. No 5 in the column, no 7 in the column. Remaining digits 2. Where's 2 in row 7? Cannot be here, here, or here because of 2 is in the column, so 2 has to be there. That leaves 5, 6, and 7 remaining in row 7. And this can't be 7 because of 7 in the column. This can't be 6 because of 6 in the column. This has to be 3, 5, or 7 there. Okay, 9 eliminates 9 here. And 9 here. 2 eliminates 2 here. So we have all the 8s now. I don't think we have all the 9s, though. We can get it, though. 9 eliminates 9 here. 4 eliminates 4 in the rest of the row. No 5 or 7 here because of 5 or 7 in the row, so that's 4. No 4 or 5 here, it's 9. We have 5, 6 as a pair here. That eliminates 5, 6 in the rest of the column, so no 5, 6 here. It's 4. That eliminates 4 in the rest of the row. Okay. Remaining digits of column 2. We have 1, 3, 6, and 7 available. Obviously, no 1s there. Column 1. We have 1, 4, 5, 6 available. No 1 or 4 available there because of 1, 4 in the row. We have a 5, 6 pair in row 4, which eliminates 5 and 6 in the rest of the row. So no 6 here, no 6 here, no 5 there. One of these is a 2. One of these is a 2. This digit is going to have to see a 6 in one of these 2 cells, so this cannot be 6. We have a 3, 4, 5. We have a 3, 5, 6, 7 quadruplet in row 5, which eliminates 3, 5, 6, 7 in the rest of the row. So no 7 here is 4. No 3, 5, or 7 here. It's 9. 4 eliminates 4 here. Where is the remaining 4 in box 4? Cannot be here, or here, or here. So must be there. Where is the 1 then remaining in this box? It has to be here. That eliminates 1 here. So where's the 1 in box 7? It has to be here. Okay. So one of these 2 has have to be 7, which means this can't be 7 since it sees that one from the same row and this one from the same box. This can't be 7. It sees both of these 7. This one's from the same box and this one in the same row. Okay. Okay, so these are definitely the paths. We just don't know about this one or this one. Okay. These are opposite parities. So we're going to make this red, blue. That makes this red. And that makes this blue. Red could be either of these, unfortunately. Blue cannot be here or here, so it has to be one of these two here. Which means blue has to be one of these three there. That doesn't help too much. If this is 6, this has to be 3. That's 7. This is 5, and that would force that to be 6. So if this is 6, it's blue. It can't be red. If this is not 6, this has to be 6, which makes this 5. That's 6. How does that work? Um, we obviously know one of these three is a 7. It's not too helpful. Um, hmm. This digit is going to have to be exactly the same as that. Which is going to have to be the same as one of these two. Hmm. So that digit is the same as that. It's the same as one of these two. Can't be here, but it could be any of these three. Hmm. Okay, what happens if this is 7? If this is 7, we have 3 here, that's 6, this is 5. That forces this to be 5 here, that's 3, that's 7. Which means 7 cannot be here, 7 would have to be here. So this would not be 7 there. Okay. That would force 6 here. Ah, and we'd have a contradiction. Because this cannot be 5, and it can't be 6. So, this can't be 7 here, which means we know what that is. This has to be 7. So we tried 7 there, that doesn't work. Therefore, 7 has to be there. That eliminates 7 here and 7 here. So 7 has to be here. No more 7 here. No 7 here. We have a 5-6 pair now in row 7. So this can't be 5 or 6. It's 7. That eliminates 7 here. This is red, so this has to be blue now. Blue, again, has to be one of those two. We don't know which. Blue has to be one of these two. We don't know which. So we have to go through this path. That makes this red. So blue must be one of those two. Hmm. We have a 3-6 pair in column 2, so this can't be 3 or 6. It's 7. That makes this 2, which means this can't be 2 or 7. It's 3. 2 eliminates 2 here, so it becomes a 6-7 pair. That forces this to be 2 over here, because there's no other place for it. Where is 5 then in row 1? It has to be one of these 2 digits here. That eliminates 5 in the rest of the box. So this is 6 or 7 here. 3 eliminates 3 here. Okay. Hmm. So blue's one of those 2, then one of those 2. Red has to be one of these 2 there. And then blue's one of these 2. Not too helpful. So what happens if we have 6 here? If we have 6 here, that becomes 5. That's 3. 6 eliminates 6 there, so it's 3, 5, and 6. That would make that 5. 6, 7. I would leave that as 5 and 6, 7, 5. That seems to work okay. 7, 6. What happens if we don't have 6 here? So if we have 6 here, 6, 5, 6, 5, 6. That makes that 3 and 5. 3 eliminates 3 there, so it's 6, which makes this 5, 3, 6. 3 there, 7 there, 5 there, 7, 6, 5. And we have a contradiction here. I'm not sure. I'm not very good at spotting these. So, anyways, we now know that this can't be 6 here. So then the reds have to be 5. The blues have to be 6. And we have to go 6 here because we need a path on this path. So this is 6. That makes this 5. That 3. 6 eliminates 6 here, so it's 3 and 5. 3 eliminates 3 here, so 6, which makes that 3. 6 eliminates 6 here, so it's 7. No 6 or 7 there, it's 5, which makes that 6. 6 eliminates 6 there, so it's 7, which makes that 5. And 7 eliminates 7 here, so it's 6, and that's 7. Experiment completed successfully. May 20th, 1975. Cells visited 32, although somehow the stats don't really feel very important anymore. Since the moment they met on Christmas Day, the 2 rats have been learning from each other and discovering more about themselves in the process. Finks has gradually gained confidence, rediscovering the zest for life that was always somewhere within her, though perhaps difficult to reach at times. Finks, too, that's why I say F and P, appears to have grown as she has helped to guide her friend on this journey. Much like their movements in today's maze, their characters have become increasingly synchronized. It has been magical to witness, and now I believe we are just about ready. And that's a solve. As you can tell, there's this thing for SudokuCon 2026, where tickets are available in Manchester, UK. So there's an ad here for Sudoku Pad. Anyways, that's the solve. Pretty cool, actually. The logic behind this was interesting throughout, and it wasn't easy throughout, but it wasn't hard. Or some of the logic might have been, well, I don't know. For example, for this portion, I just basically just resorted to basically plugging in a number and then trying to get to a contradiction. But there's probably just some normal regular Sudoku solvings that you can use to be able to solve that. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.